Greetings, Earthlings! Before we start exploring, don't forget to like, comment, and subscribe, wherever you're listening. It helps more people find the show and supports our mission of making science accessible to everyone. You're here with DJ Stellar Cloud. Thank you for tuning in. And welcome back to the Exploring Your Universe radio show. You're here with DJ Stellar Cloud, she, her.
I am DJ Cay, they, them pronouns.
I am DJ Ray, any pronouns.
DJ Cay and DJ Ray, aka Casey and Rayner, are both graduate students here at the UCLA Physics Department, and they have both been volunteers side by side at Exploring Your Universe for these past 2 years. As a reminder, Exploring Your Universe is UCLA's largest science fair. Every year we get over 12,000 visitors, and we have over 500 volunteers. We are so lucky to have two of our favorite volunteers here with us today. They are my favorite because every year I get to pair them right next to each other, and it's really nice to fill two spots of a booth at the same time. Okay, so let's go ahead and get started. Y'all have volunteered at 2 different booths now. What are they?
Okay, so we have volunteered in 2023 and in 2024. So in 2023, we were in a booth called Explore Earth's Surface, and this was with Professor Solgi Moon. So this booth had a lot of things going on. It was like a full room with like 4 different things, and there were a lot of different volunteers. So
this is one of the indoor booths.
Yeah, this is one of the indoor booths. So there were 4 things that I can remember going on in this booth. I think that the most exciting one that all of the kids love to engage with is the meandering rivers simulation. I don't know what she calls it herself, but basically it's this giant sandbox.
Yeah.
And the idea is that like we're supposed to simulate how rivers meander. Like I'm not personally a geologist, so
I'm not either. I know I work in the geology building, but I don't know anything about geology. I got a B in Silgi's class, which as people will know for a grad student means you didn't pass. But anyway, the big sandbox with water.
Yeah. So the idea here is that we're trying to simulate how rivers meander. So basically, rivers don't like to flow in a straight line because that's kind of an unstable equilibrium state for the river. So the moment it gets like a little bit perturbed, the river actually starts to bend and meander.
Yeah.
Right. So basically, this giant sandbox is supposed to simulate the way that rivers meander. So I think like the top, there's like some water and it like drips down to the bottom, and as it drips down, we can see like the bends of the river begin to form.
Yeah. So an unstable equilibrium is kind of like you're walking on a tightrope in which you are allowed to balance on the tightrope, but it's probably super hard to keep yourself there, so you're more likely to fall down, which in this case would mean that your river is meandering.
Yeah. It's just like I like to imagine it like a ball on the top of like a bowl. Like if the bowl is like concave up, then it's like a stable equilibrium, but if it's like flipped upside down, you put the ball on top. Not as stable to be on the top of the bowl.
I like how your metaphor doesn't include people falling down.
Yeah. You can imagine the ball as a person. Okay. A little bit more anxiety inducing.
Yeah.
But
we're clumsy out here.
But basically we try to like encourage the children to play with this simulation of this river, and we were like, oh, look at how the river flows. Let's see what happens when like you put a rock in the way. But of course, like these children, they're most excited about giant sandbox, big water, rocks everywhere. So like I think like the first half of the day we were trying to convince them to be like, oh, look at how the river flows, like what do you think happens? But at some point we just all gave up, and they just like want to build a dam. Like every child wants to build a dam.
They wanted to stop the water flow so fast.
Yeah, so
the beaver instincts.
Yeah, the natural child beaver instinct is always coming out with these children, and like I don't know, they all like work together and they like try to build a dam. It's fully unrelated.
That's so funny.
It's so funny because like we can see them like fall into like the same type of thing. They like build the dam, and then they see like there's like this thing that we use to like clean the basically flatten the entire sandbox.
Right.
And that is always like the point of weakness of the dam, and they always like spend 15 minutes building the dam, and then like some kid will pipe up, be like, this is the weak spot, and then they all like,
oh my gosh,
yeah, like it's like it happens again and again. And I think it's so sweet that like this is definitely not the original intention of like the experiment or like exhibit, but
it's auxiliary science.
Yeah, they're like they're using their like senses, they're like observing, they're engineering, and like they're actually like a lot of them are working together to build this dam. And I thought it was like really sweet, even though it was definitely not a meandering river.
I think it's like really interesting because like you're saying that it's engineering, right? And I think that it's like these kids, I mean, they're kind of like messing around, but they're also sort of like intuitively learning. Like they love to learn
100%, yeah,
and they want to see like how things react and behave, and that's like a natural curiosity. And it's not just, you know, originally we were supposed to show them and kind of teach them things directly, but they have this tendency to like go and learn on their own, and I think that's like really cool. Yeah.
They're really exploring your universe. For them, the universe is a sandbox, but it's been explored. I love that. Also, Sulky is a parent, so I'm sure she understands that kids are just like going to do that kind of stuff. Yeah. Anyway, I know listeners can't see this, but we're in the room with like a bunch of sandboxes right now, and oftentimes when I come in here, I am also very distracted by the sandbox. So I get it. Okay, you said that there were 4 things that happened at Sulky's booth.
Yeah. Speaking of the sandbox, there was another sandbox. So I guess like the first one, the meandering rivers one is more like kind of like muddy a bit more, but like this one is like fully dry sand. And basically it's I don't know how to describe it in like the geological terms because
I don't either. It's okay.
But basically it's like this giant sandbox, and when you like change the height of the sand, it can like show the equipotentials. I feel like that's like the more physics term of it, but like they have like the contours where the sand pile is the same height.
So I think we call this a topography map.
Oh, yeah.
And the idea is that the higher your mountain is, the more rainbows you get. And then if you have something that's totally flat, it would all be one color.
Yeah, exactly. So I wasn't like directly involved with that booth, but it's like really interesting because it's like kind of high tech, and that you can see
it's very
like
high tech.
The kids like really they love to like build stuff. They make like the smiley face and like the pit. It's like a really fun thing, and I see it like literally across the room right now.
Yeah. Okay, so we've now dealt with 2 of the indoor things. There's 2 more?
So there's 2 more. One of them is something called a critical zone, and to my understanding, what a critical zone is kind of like the interface of the Earth and like basically like human and like ecological life. So I'm not like, of course I'm not a geologist, so I'm not the best at explaining this, but I think that this part of the booth, there was kind of an issue with it where the things that we ordered did not come in correctly. So I think that the original idea is for the children to create their own critical zone. Okay. And I think we ordered rocks, but they were kind of like the you know like the rocks you get in like the tourist destinations.
Yeah, the decorative, colorful rocks.
Yeah, I think we got those by
accident. I know what these are. They're the ones that look like chocolate.
I think so.
Okay.
I think so.
DJ Cay is talking about something that I have inventoried like 6 or 7 times now. I still have them. If anybody wants them, they can't be used by the event, and we need to donate them. So I know exactly what you're talking about. What kind of rocks were y'all hoping to get?
I have no idea because I just showed up that morning. But whatever it is, that was not the original intention. And I was there with Professor Moon, and we were like, what do we do with these rocks?
Yeah.
And I used to volunteer a lot with like children and like when I was in high school and like, you know, before I was like a grad student here. So I know what kids are into, and I know that kids love to dig.
Yes.
Okay. Kids absolutely love to dig. So I was like, okay, what if...
That's how they get their damn material.
Yeah, so I was like, what if we hid these rocks in a bunch of sand? Gosh. And then we were like, okay, and then they can like dig for the rocks and be like, oh, did you find a piece of like, I don't know, like amethyst or something, or like a piece of, I don't know, like tiger's eye. And I was like,
this is so funny.
Yeah, and then it was yeah, so what we did, we got like a box, and it was really interesting because I learned that there's some sort of like geological sand that they use to study. I don't know what they exactly used to study, but it's supposed to be like different.
It's like fineness.
Yeah,
right? How fine your sand is.
The different grains of sand are like different colors, so you can like see like if they settle in a different way. I'm not a geologist once again, but like we basically buried it in this sandbox, and we threw the rocks in, and like sometimes I'd be like, oh, do you think that there's something special with the sand? And they'll be like, no, it's sand. I'd be like, no, it's not. It's like special sand. And then I would shake it, and then you can see the sediments like separate. So this like critical zone part of the exhibit was initially going to be like a huge failure, but I feel like it was kind of a moment for like the kids loved it. First off,
anything with sand and rocks and digging, they're gonna love.
Yeah. And it was like I thought it was interesting that like kids actually really enjoyed engaging with it. That's what I keep on learning, is that they always engage in ways we don't expect them to, and I thought they had a good time, even though they definitely did not learn about the critical zone.
There was a poster,
but
if they wanted to read it.
I feel like I didn't read it, so
it's okay.
I have doubts that the children read it, but you can cut that out because I'm a good grad student.
No, a lot of the children can't even read, so it's fine. Like, having these hands-on experiments is really like the core part of BYU, and like letting the kids actually like put their hands in some dirt and mud is really part of it. Sorry to all the parents' cars.
Yeah. I remember at some point during the day, like one of the parents were like, these volunteers have so much patience, and like they'd be like throwing mud at like the not landslide, like the meandering rivers. It was more like a landslide at that point, but yeah, we had a lot of patience that day. There was a lot of noise, but it's always very rewarding. But there was one last one.
Okay.
As like a physicist, I don't know what the geological intention was but to me it was more of like block on slope, like the very classic physics problem that every
block on a wedge.
Block on a wedge.
Calculate mu.
Yeah. And basically it was like a wedge or a slope, and there was one version where there was sandpaper and one version that there was no sandpaper, and basically they were just supposed to like, see which block would go down the slope, and maybe the listener can like kind of imagine what would a child do with this type of setup, and it's of course not to like patiently like drop the block down the slope. They were sanding all the blocks. There was so much there was so much like sand dust. Like, what is it called? Wood dust?
Sawdust.
Oh my god. Yeah, there was so much sawdust.
Wait. No, that's actually so funny because like it's like calculate mu, and the kids are like, no, I'm gonna change what mu is by sanding the block.
But yeah, it's like just like this entire booth demonstrated to me that like kids will always like find their own way to explore the world in like ways that even I wouldn't expect, that I wouldn't have originally imagined. And like, a lot of them learned a lot of science, a lot of them learned a lot of engineering, surprisingly, and a lot of them, I thought that they all got something nice to take away from the booth.
That's great. Some sawdust, some mud. The sandpaper has also been rejected. I find it by accident all the time floating around the room when I'm moving something, and I'm like, ow, it's always like this sandpaper.
Yeah.
I think they're like, let's never do this again.
Yeah, so that was the 2023 booth, and you can describe the Spin Lab booth that we did.
Oh, the Spin Lab booth. The Spin Lab booth was a lot of fun. Again, we just showed up on the day.
Yeah.
We didn't really know what was going to happen, and then like the professor basically just said, "You'll learn. You'll learn as we explain things and as we do these things." And we really did. I think that like even as a grad student going there and managing this booth, like I learned a lot about physics.
Mm-hmm.
And I saw like a lot of like parallels to like the things that I had learned on my end of physics, whereas this was like atmospheric sciences, and I do research in plasma
sciences. I think it's planetary interiors. So Spin Lab stands for Simulated Planetary Interiors.
Oh.
Yeah, which we learned on the Brandon Lazard episode just a few weeks ago. So no worries. I also didn't know that.
Just learning about their setup,
I
could see a lot of parallels to like things that I'd learned in my time at physics. And
did you study physics in undergrad?
I did.
Okay, so you've been doing physics now for like 6 years.
It seems like forever, all the way through high school.
Okay.
And so like I'd been doing physics for a long time.
Yeah, so you definitely ran into more than one angular momentum problem before.
Oh yeah, for sure. For sure. Last time we did the sand, and sand is like something that kids love.
Yeah.
And what is the next thing that kids love? And it's water. And so this was a whole setup about
pool.
water.
Yes.
There was this big tank of water, and there was this little spinning table that they set up outside, and we sort of spun the water in a circular, like some kind of circular tank.
I've been calling it a kiddie pool very unprofessionally.
Well, maybe the next time the kids will jump in, but
Yeah, don't encourage
It
them
looks
on that.
really uninviting. It's full of food coloring and like
Oh yeah.
yeah, in the end they put in a lot of food coloring, but it's like really simple because you just take a body of water and then you rotate it until it reaches what you call like solid body rotation. Now, I'm also not part of Spin Lab, so this is to my understanding, but we just rotate this body of water. At some point, the water will start to spin as if it is a solid object, and that's called solid body rotation. Because, when water sort of like moves in a way where it's like moving past itself, so there's like different velocities or different angular velocities or different velocities next to each other.
Yeah, like if you're running in a race, like the smaller labs are different sizes from the outer labs.
Yeah.
Right.
Yeah.
And so when if water starts to move past itself, there's like viscous force.
Yeah.
And so if you wait a long enough time, the water will sort of arrange itself such that it moves like a solid body where it's not like shearing past itself.
Yeah. That's really cool. I didn't realize that.
Yeah, it's really cool. When we look at this setup, it's like a solid body rotation. It's like just a body of water that's spinning.
It's not swirling anymore.
It's not
like
swirling
a disc,
anymore.
Yeah.
Exactly. And just by perturbing it in like really small ways, you see that you would expect that like, if it's just spinning and it's just as if it's still water again. But it turns out that when things are rotating, like the Earth is rotating, when things are rotating, you start to experience some really interesting phenomena. And so we had a shallow, like, sort of wide tank, and we had, like, a tall, like, narrow tank.
Yes.
And in the tall, narrow tank, the main thing that we wanted to do was we wanted to simulate tornadoes.
Yes.
Which was really fun. And so what we did was we had these little Alka-Seltzer, like, tablets. And we would demonstrate, and we would get the kids to try it as well, where we threw the Alka-Seltzer tablet into this tall column of spinning water, and when the seltzer started to bubble and started to like convect and push water up through the tank, you would see that a tornado would sort of start to form around the Alka-Seltzer, which was really cool. I didn't really know why that was, and I was learning alongside the kids, and the professor explained it, saying that when you push water up, basically what you're doing is in order for there to be some kind of upward column of flow of water, you need to pull in water from the sides as well.
Yeah.
It's difficult to like explain without drawing some kind of diagram.
So you start to build this like circle where the water is moving on the sides of the tank, but also going through the center, and so it's making like loops.
Right,
Yeah.
exactly. But the key is that like we're drawing in, because we want to have some kind of upward flow.
Yeah.
The water has to come from somewhere.
Yes.
And so we have to draw in water from the sides, and all of that water contains like some amount of angular momentum.
Yeah.
And so when you're drawing in angular momentum and you're condensing it into a space of smaller radius, you would expect it to spin faster.
Yeah.
It's the same way that an ice skater, when they start to spin slowly and then they pull themselves in, they pull their body, their limbs in, and then they start to spin faster. And it's the same principle where when we have this inflow of angular momentum, we start to see the tornadoes form. I think it was really, really interesting. And we saw like other types of phenomena in the big tank, where I think that they put in droplets of dye into this big spinning tank.
It's food coloring, by the way, 100% safe. If your child licks the tank, they will survive.
Yeah, no, and and then they were touching it, of course.
Yeah.
People were getting wet, but
you put in this dye, and it would like form this little like vortex kind of, like almost like a little loop. And that was really interesting as well, because if you just put in dye into a non-spinning pool of water, it would just dissipate, right? Whereas in this case, because it's spinning, it sort of becomes localized into into some kind of column. And so, I was learning a lot alongside the kids, and I'll tell you more about what the kids did later. But just like a fun physics fact is that, and I was talking to, the professor and people who knew more.
Professor John Arnaud, by the way, for anyone listening.
And the people who knew what was going on, right? So Professor Arnaud, and also I think Brandon was there.
Yeah, Brandon, who's on episode 1 of season 2,
which I knew from I knew from plasma class, actually.
Oh, you guys know each other.
So we sort of were acquainted already.
Okay.
But they basically, they were explaining to me these things, and Professor Arnaud told me that, in a spinning frame, when you're spinning, so like right now, if you're living on Earth, which I assume you are.
Hello, E.T. They have finally found me.
If you're living on Earth, you're living in a spinning frame of reference, because the Earth is spinning.
Yes.
And in spinning frames of reference, spinning frames of reference sort of act similar to magnetic fields in that, like charged particles and magnetic fields.
Yes.
Like that kind of physical dynamic is similar to like spinning frames of reference.
QB cross B.
Exactly.
I remember, yes.
And the B cross V thing, the cross product, you would see that in the Coriolis force, where there's like an omega cross V.
Yes.
And so instead of B cross V, there's omega cross V. So like that's like kind of the math of it.
Yeah.
But in a more intuitive sense, if you imagine like what happens to a charged particle in a magnetic field, I'll just tell you if you're not like acquainted with physics. But like what happens to a charged particle in a magnetic field is that it goes in a little loop.
Yeah.
Right? And so you can imagine that, like, if I followed the loop, right, it's as if the magnetic field doesn't exist, right?
Oh, and if you were also in the loop with it, you wouldn't notice.
Right. Yeah. If I went on a loop with the particle, I would sort of remove the magnetic field, because I'm just the particle to me, because I'm going on a loop with the particle, is stationary.
Yeah, because that's why we don't feel like we're constantly spinning on Earth.
Right. Yeah.
And
then if you do the opposite, where you start to rotate your frame in the other direction, you would think, oh, the magnetic field is a lot stronger or something like that.
Yeah.
And so like there's this really interesting thing where, spinning frames of reference have this sort of like pseudo magnetic field.
Oh, that's really funny. Okay.
But that acts on non-charged particles.
Yes. Okay, to anybody who never wants to take special relativity, you only need to listen to this episode, and I think this is all you need to know. This is all I know, and the great University of California, San Diego gave me a physics degree.
Accelerating frames of reference are too much for my brain to process.
Yeah, it's a lot. But anyway, so there is so much science to be done at the Spin Lab, but the Spin Lab's also like this really picturesque thing. It's on the front page of so many people's photo albums because there's the big tank with all the colors in it. Do y'all feel like the kids learned something great there?
I think it's a little bit hard to explain with the angular momentum stuff.
Yeah.
But like, I think that like physics is also like about gaining your intuition, and you sort of draw comparisons between things. So the best intuition we could give them is like, oh, you imagine like an ice skater who's like spinning and then it's pulling their limbs in, and that's what causes the tornado to form. It's kind of hard to explain like magnetic fields and cross products because they haven't
taken vector calculus.
They haven't taken
What
vector
is wrong
calculus.
with these kids? All kids want to do these days is not take vector calculus, and we're tired of it.
Yeah, absolutely. But what they wanted to do was when they looked at that big tank with the tornadoes, they were like, how many Alka-Seltzer tablets can we put in this tank?
You guys keep running into like the craziest booths.
Yeah, I think that for the taller rotating column, I think that like the pool with the dye in it, there's like a lot of like interesting dynamics that are like very, very advanced that like I don't think I can like give any sort of justice to.
Okay.
So like there's like a lot of advanced stuff going on there, but like at least for the I think that specific exhibit was more about like you can see these like interesting dynamics, but not really about explaining the physics.
Yeah.
And then the taller rotating column that we were simulating the tornadoes in, what I like to do with the kids is I ask them, like, what do you think is going to happen when we throw this Alka-Seltzer in? Like,
forced intuition, yeah.
Yeah, and then they're like, do you think it's going to be a tornado? Do you think it's going to be like a column? Like, do you think... And then everybody's going to be like, it's going to be a tornado.
Yeah.
And I'd be like, okay, what kind of tornado? Is it going to be faster than the rotating frame, or is it going to be slower than the rotating frame? And they're going to be like, slower or faster. Like, there's a whole bunch of like different answers. And then I'll be like, okay, guys, make your guesses now. And I like pass around the Alka-Seltzer, and then we do like a big countdown, and everybody throws it in. And
everybody throws it in at once too. There's like 10 kids.
Yeah, they want to throw in like the entire tablet. Like I usually break.
Want to.
Yeah.
But also we run out of Alka-Seltzer tablets every year. This is probably why.
Yeah, no, they love like throwing it all in, and like I think that like, the smaller bits look better, but like when you have like the $50 sized Alka-Seltzer that kind of spins like a coin, that's also pretty cool. But yeah, I like to like engage with them and like what do you think will happen, and then like the people who got it right, they like, you know, they're kind of like rewarded, and the people who don't get it right, they learn something new. Right? So it's always like kind of like a win-win situation, and you throw the bubbly thing in the big water column. So like
DJK, are you a physics TA?
I'm currently not a TA, but I've TA'd for 2 years, and I used to TA like the very large like intro physics classes. So I have a lot of experience explaining a lot of these topics too, like kind of not like, I don't like to use the word like dumbing down, but like kind of like simplifying it for like to like have everybody understand the material, like
making science accessible. I was just asking because your like teaching strategy of making everybody guess before they do the demonstration is like very teaching a GE coded. This is exactly how I teach my GEs too.
No, DJ Ray is actually TA of the year.
TA of the year is in the house here at the Exploring Your Universe radio show. Oh my gosh, you guys, absolute royalty celebrities. What class were you TAing?
We used to both TA 1B, so we used
1B.
to be we always like to do everything together, but no, if you see DJ Ray's like TA reviews, I've seen them. I've seen them with my eyes, and they write fan letters, they write essays, like this person is allegedly a celebrity.
I was trying very hard, I think.
Yeah, no, I believe that. You've got the courage. Okay, what is 1B?
1B is so there's like a 1 series sequence that all of the engineers and like physicists, like the STEM majors take. And basically like 1A is like mechanics and like rotating type of stuff, like, you know, angular momentum type of stuff. And then like 1B is more, it's kind of like a hodgepodge. There is like Bernoulli's principle, so like and there's like wave mechanics, and mostly I think like my favorite
like I think magnetic
and
electric.
My favorite half of it is like Gauss's law and like E&M, because like I feel like the intuition of that is like very rich, and I get to use like a lot of stupid analogies.
No, I'm an E&M girly. I say this to my partner all the time. My partner, who by the way has never been on the radio show with me, shout out to him, what the heck. I'm always telling him like I'm such an E&M girly because I love Gauss's law and doing all the vector calculus, but it's not everyone's favorite. Anyway, on to the next. You guys do everything together. How long have you been together? Where did you meet?
Oh my god. I've always wanted to answer this question.
It's like the Meet Cutes NYC thing.
Yeah,
we were always like, oh, we wish that we were on that.
Yeah, we always like fantasize like, what if somebody on the street asked us how we met? But do you want me to tell the story? Do you want to tell?
You should tell the story.
Okay, I'll tell the story. So we are both in the same cohort in the UCLA Physics Department. And in our first year, we started dating. But the secret is that you confessed to me, and I rejected him first.
No.
And it was like, it was so sad. It was like we started our relationship with a breakup because basically.
How does that even happen?
Yeah, like basically,
We're
I was
like good friends, right?
we were
Okay,
pretty good
okay.
friends, and like I think my mind has a really good job of like separating like friends and like romantic interests. So I never like considered you in that basis of concepts before, and then
Okay, DJK is saying basis. This is a thing in physics where it's like realm. It has nothing to do with being basic or like the lowest level. It's like this realm of friendship versus relationship.
Yeah, exactly. So basically I was like, this person's my friend, and then like this entire quarter you're like, oh, I feel very sad, and like I just want like some space for myself, but like you weren't angry with me at all. You're just like, I just want like some space for like, you know, mental health. And I was like, okay, sure. And so like for an entire quarter we did not talk. And we used to sit next to each other for every class.
Oh.
And
we
then
stopped
sitting next to each other. So you would sit in front of me, but then I would look at you every class, and I was like, actually, wow. and then I think like the biggest thing that made me decide, I was like, I think I need to like, you know, I think this person is like very promising, and like, you know, like somebody that I think is like truly like a kind-hearted person was when I saw how he TA'd his students, is that like he really takes time and energy into his students, and like the way that they, you know, like the way that they latch onto your teaching, and like how you take care of them and how you like think about their needs is like, I'm like, wow, this is like somebody I've never like met before who's like so thoughtful and so kind about
I'm gonna
other people's
cry.
needs.
I'm gonna cry. DJ
Yeah.
Ray is gonna cry.
I'm gonna cry. Everybody's crying. But yeah, it was like it made me like seeing how much you cared for the students and like how good you are at teaching made me realize that like, you know, you're like one of a kind.
Aww.
So after
I need to leave the room, you guys.
yeah. So after that quarter, we got together, and like pretty quickly we knew it was gonna work. And you know, it's
been 2 years.
It's been 2 years. We're about to have our anniversary next Tuesday. So
Oh, happy anniversary.
yeah. So you know,
it's so fun. It's just like it was like our birthdays as well. So
yeah. So
Oh, really? Okay.
So it's like your birthday. Your birthday, and then I think 10 days later is my birthday, and then 1 week later is our anniversary.
Yeah.
So it's always.
Yeah. So yeah, April.
Busy time for you guys.
Yeah.
Thank you for taking an hour out to come talk to me.
Yeah. Yeah.
That's really sweet, though. I was told that y'all were dating in like December of 2022, so this must have been like pre-initial breakup.
No. I think it was.
Yeah, we started dating in 2023.
Yeah.
Yeah.
Actually, so
Okay. So somebody told me, like, they just predicted that y'all were gonna be together, I guess.
Oh, wow. Who was predicting? Somebody had foresight.
I don't think I'm allowed to mention this person.
Maybe he was predicting. He was manifesting.
Okay, so what's it like being like the UCLA physics like couple? Because I don't know any other like couples who are like same cohort.
There are actually quite a few.
There's like quite a few, but like there's some stark competition.
Really?
Honestly, there's some pretty good couples in physics, in my opinion. But, you know, obviously, in my opinion, I'm biased. I think that we're the best. And I
you
think...
guys are my favorite couple. You're the only couple who's ever been on the podcast. So the rest of them...
Yeah. But I think the interesting thing about, like, being in, like, the same field and also, like, you know, being in a relationship is that, like, we provide, like, very different ideas in discussing physics.
Oh, okay.
And I love talking about our research because if we like look at like what our research is like both of us kind of study emergent phenomena of many-bodied systems, right?
Oh,
so
that's funny. Okay.
But my specific research, which is condensed matter physics, is one limit, which is like very cold limit, where we are looking at emergent phenomena in solids and like materials, and you work in the complete opposite realm, which is plasma physics, which is also like a many-bodied system, but it's like very, very, very hot. So we're cold and hot, I guess.
I love that. That's so cute. Can either of you touch the things you work on, or are they?
No.
I've never touched my crystals before because I'm a good scientist.
Okay.
But
you 100% can't touch plasma.
No, because the plasma that I work on, I guess I'll talk. We can talk a little bit about what we do. But like the plasma that I work on is at the NIF, the National Ignition Facility. If you don't know what the National Ignition Facility is,
go ahead and explain.
It's like it just imagine like there's this huge building,
mm-hmm.
and half of it is filled with lasers. So just imagine like a building, and then like all of it is lasers.
Yeah.
And then they channel all of these lasers into the other half of the building, which is a huge chamber, like a kind of a spherical-ish chamber.
Okay.
And all of the lasers in this building point at one tiny spot, like in the center of the chamber.
It's like the Thunderdome. Like everything's just like attacking this one thing.
Yeah. So you have this big sphere, and at the center of the sphere, they put targets.
Okay.
And then they blast the targets with the strongest, the most powerful lasers in the world, essentially. And that takes the entire building to generate all of these lasers, and then they blast tiny pellets. I think my target is like a centimeter.
Oh,
and
it's over for that target.
But the key purpose, because this is not my research, but the key purpose of the facility is to study nuclear fusion.
Okay,
so basically trying to get things hot and dense enough to have nuclear fusion occur.
Nuclear fusion could save the world, by the way, to anyone listening.
The likelihood is debatable, but it could. It really could. And my target is really actually to simulate space phenomena. And it's really interesting because like plasma physics, a lot of the physics in plasma physics is sort of like miniaturizable.
Okay.
Because
you don't need the whole sun to learn plasma physics.
Right. Yeah. So, what matters in plasma physics is this, like, what we call the scale lengths of the plasma.
Okay.
And if you have plasmas of different temperatures and densities and magnetic fields, like, the scale lengths change. And so we can, using higher temperatures and higher densities, we can simulate, like, huge, extraterrestrial like nebulas. We can study those by like miniaturizing them.
Yeah, so scale length is like what is the smallest amount of this thing that we can have and still learn all of its properties?
Right.
Okay.
Yeah, and that's a good way of putting it. But so we can sort of miniaturize like things in space and study it on a smaller scale. And what we're doing is we're studying like shock waves in plasma. So that's what I do. You can probably expect that if you shoot a bunch of the most powerful lasers in the world at a pellet that's about 1 centimeter, it's going to be very, very hot.
Yes. Where is this building so I can avoid it?
I think it's in California.
Have you visited it before?
I have not.
Okay.
I did not manage to. I was away, but I will be there for the next shot. But the next shot is like in a year.
Okay. Yeah. I think one of the hidden things about physics that people don't realize a lot is like you do an experiment one time, you're using that data for like 2 or 3 years. Are you guys also similar in that?
So my type of experiment, so technically we're both experimental physicists, but
okay. Would you like to give us a brief definition of what an experimental physicist is?
Yeah, so an experimental physicist is that we it's quite literal in that like we do the experiments, and sometimes we work with theoretical physicists that like sometimes they have like an interesting prediction, and then we say like we can figure out a way to take a look at it, or we can also like find like new types of phenomena, and then we also like do data analysis on like all the data. Like we're the ones running the physical experiment.
Yeah. So there's some guy somewhere in a closet with a pen and paper making all these ideas, and you guys bring those ideas to life.
Yeah. I mean the separation is not like that. Sometimes
especially in our field.
Yeah, in our fields, like sometimes the experimental people and the theoretical physics they work together.
Okay.
A lot. Like I think that like in high energy physics it might be more differentiated. So,
right.
But like generally like they're 2 different sets of skills, and like especially with experimental physics there's so much stuff about like instrumentation, like understanding like the limitations of your equipment, like how do we like I deal with this a lot because I also work on lasers, except my experiment is like pretty short. It actually, some experiments in my lab last for like femtoseconds. Like that's very, very small number.
Yeah.
Right? And like basically this experiment is like on like such a very, very tiny length scale. And like your experiment is also technically on a very tiny length scale. It's just that like it takes a lot of energy to do the experiment in the first place, but like my experiment is like on a tabletop in like a basement in my lab.
That's probably one of the biggest differences, because like I think to your point just now, it's like my experiment is you get one shot every year, and then you have to deal with the data from that shot for a long time. But your experiment,
I'm always pumping and probing with the laser with like all day, all night. Like it's like almost like a little bit like physically straining, because I have to like I heard from like I think like my PI has like a story where one of his lab mates had to get like back surgery or something from like working so long on the optical table. I'm trying to avoid that.
File that workman's comp lawsuit.
But it's pretty intensive, but like I can take like a lot of data, and it's more about like my physical body and like my time and like, but
do y'all know David Garcia?
Oh yeah, David Garcia.
David Garcia on a previous episode described how he's been tuning like the same laser for like a whole year now.
Yeah.
Sounds about right.
That sounds about right. That's like the reality of like experimental physics. You're like, oh, you just shine the laser and you collect the data, and then you do. No, that takes a year. That takes a year.
Absolutely.
Like you need to order the equipment. You need to order the right filters, the right polarizers, like the right like camera, or like right, you know, like photo multiplier, whatever, like whatever like instrument you need for the experiment. It takes like a long time, but I can like talk a little bit about my work, which is on like photo-induced phase transition. So I work on condensed matter physics. So the way I like to describe it to people is that it's basically material science with like more sprinklings of like quantum mechanics. But the work that I personally do is on phase transitions. So
condensed matter physics, so plasma is like hot physics. Is condensed matter cold physics or something a little different?
On like the length scale, it's like a lot colder than plasma.
Because you have
like,
a cryostat.
Yeah, I have a cryostat, but like it's there's like a lot of phenomena that like we can only observe at like really low temperatures, like Bose-Einstein condensates and like a lot of these like other types of things. But like my like temperature scale is like more like room temperature, depending on like the temperature of the phase transition, right? Which is a lot lower than, I mean, like plasma is like super hot, right? Like I'm like definitely
like not touchable.
Yeah, it's like I'm on like room temperature down to like a few Kelvin.
Yeah, I can touch the room.
Yeah. So my work is on phase transition. So like perhaps the listener might know of like you know, like ice and water and like water vapor.
I hope our listener knows about ice and water.
Yeah,
when you freeze water, it turns into ice, and we call this a phase transition.
Yeah.
So this is what DJK studies, but at a much more difficult level.
Yeah, so there's a whole lots of like different types of phase transitions that are out there, and like the way that physicists like to describe these phase transitions is something called spontaneous symmetry breaking. So what that means is, let's take like water for example. If I were to like be like a little camera inside the water, and I were to like point my camera in different angles, and I were to time average all of the water particles in the fluid, I would say that like, oh, the fluid looks pretty much the same in all directions. And if I were to translate my camera to a different location, I'd be like, oh, the water looks pretty much the same.
Translate meaning move.
Yeah.
Same language of camera.
Yeah. So what we describe this is isotropic for the angle and homogeneous for the translation, right? So we would describe the water as isotropic and homogeneous for the time averaged water particle location. But if you were to look at ice and you were to freeze it, it turns into a crystal, right? And you can imagine if you're in a crystal, if you were to look at different angles in the crystal, you're like, oh, this is actually a different location. I'm either pointing to like a corner or like an edge or something like that. Like you can imagine that you are able to tell where you are, where you're pointing based off of the lattice.
Yeah.
And so in a crystal, like you can only point at like certain directions, and you can only translate certain amounts of distances in the crystal to return to the same location. So in that way, we started with something that is isotropic and homogeneous to something that is only discrete. They're like discrete rotational and like translational symmetries. And that is what we describe as symmetry breaking. And it's spontaneous in that like it only happens at one specific temperature. So basically we describe a phase transition as any material that exhibits this spontaneous symmetry breaking of some sort, right? So in water, it's like water to ice. It's like the crystalness, like it forms like a crystalline structure. People might know about magnets, right? Like ferromagnets, like when you like cool it beneath a certain temperature, all the spins align in a certain direction, right? So once all the spins align, we say that like, oh, suddenly before all the spins are randomly aligned and now they're all in the same direction.
Spins are which direction your electron's pointing. If you get a little bit lost there, it's fine. The point is magnets start to become more and more organized as their temperature changes.
Exactly. So what I have been looking at, I look at like a variety of phase transitions. So the material that I've been looking at has like an anti-ferromagnetic phase transition, which is like basically the spins point up, down, up, down, up, down. There's also like a few other ones I look at. Like I'm probably going to look at like a ferroaxial order. That's a little bit more difficult to explain without like a picture, but basically I look at like how these phase transitions evolve and like, you know, like potentially even like photo-inducing it, and like I use like a specific technique called second harmonic generation, which is like that might be a little bit to go into.
Photo-inducing means we're going to shine a light or a laser at something and it's going to change. It has nothing to do with taking pictures. Photo as in photon.
So basically in second harmonic generation, we shine in like 2 photons, and what comes out is 1 photon.
So like you guys.
Basically like we shine light into a crystal, and the frequency gets doubled when it leaves. So like basically like the wavelengths that I look at is basically it starts as like almost infrared, like the wavelength is too long to even be visible, but once I shine it past a crystal, it suddenly becomes blue, right? So it's like it's kind of this process that like transforms this light, like basically doubles the frequency of this light and
changes its color.
It changes its color. But the interesting thing with this light, and the explanation is a little bit more esoteric, but the bottom line idea is that the leading order term of this light, like the largest contribution to this light, is something to do with the symmetry breaking of the crystal.
Oh my gosh.
So
that's crazy. So you're in a hall of mirrors and like basically and all of your reflections add back onto you, and now you're like more than the person you came in as, and that had to do with the fact that the mirrors formed at a certain temperature.
Maybe.
Oh my gosh.
I'm not. The idea is that this fancy thing where 1 photon becomes 2 photons deals with the inversion symmetry breaking of the crystal, which might be a little bit more esoteric, but the bottom line idea is that I use this fancy nonlinear optical technique that can look at how the symmetry breaks in the material, and when the symmetry breaks in the material, that is a phase transition. So
cool.
I'm sure that like you can tell, but like both of our experiments, it's kind of like hard to talk to like a young child about, and like I can't really like shine a crystal, like shine like a laser, like blast a laser in front of the kid, be like, look, it's blue, because like
so they don't have safety goggles. They don't have enough funding.
Exactly. I fear for my life sometimes because even though I'm very fearful of the laser, but like I would not trust kids around it. But I think like the really great thing about EYU is that like we have the opportunity to like, you know, engage with like young children about research that's not like directly related to our research. So it's like kind of like a double win, right? Like we learn more about like the broader world of like research and like what is out there, and we see like connections with our own research, and we still get to like engage with like the younger generation about science. And I think that's why we both love EYU so much, is that this is like kind of a once in a year opportunity where we get to really feel connected and like a part of the larger scientific community, versus like the rest of the year, like all 364 other days, I'm like blasting lasers in a basement.
And it's like a really dark room.
It's a very dark, loud room, and it's a little bit terrifying because like some of the lasers, they're very high power and they're not visible. So like it's a little bit terrifying, and it's like a little bit dreary, but you know, like, and then I go out into the sun, I play with the kids, I like, you know, I make like a mud, like a dam, like a mudslide or something.
Well,
and,
you
like,
didn't make the dam, they made the dam.
They made the dam. I politely
supervised
it, made sure that nobody got hurt. So
No, that was wonderful. And weirdly enough, we've brought it full circle to how we normally end the episodes. It's if y'all were children at EYU, picture this, you're at EYU, you went through some crystals, so there's actually 2 of you now, and there's a small version of you as a small child and you as an adult. What would you have wanted to hear as a small child at EYU?
As a small child at EYU.
Or like a regular sized child.
A regular sized child. I was probably on the smaller side as a child. I think that's a really good question, and I think that the joy of being a child is that like you kind of like go into this thing not knowing what to expect, right?
Yeah.
And like I think like the biggest reward is not like getting some sort of specific type of advice. It's kind of like exposing yourself to things you would have never expected or experienced before, right? So I feel like I don't have any sort of like curated or like specific advice because I feel like the mentality of like being a scientist is just like being able to like observe and like gather new ideas from it. And like I think that my younger self did a good job bringing me to like wherever I am. So maybe I just like have trust.
Yeah,
my
you were
younger
just a really
version.
good child.
Yeah, I was just brilliant, smarter than everybody else.
Yeah. Perfect. Everybody loved you on Impact. Okay, what about you, DJ Ray?
I think I would just, as a child, I would probably just let my curiosity guide me. I think I would just want to know. I think as a child, I really wanted to know it all. More than I do now, I think. Because I realized that there's just too much to know, and it's kind of overwhelming. But I think as a child, I really wanted to know it all. I really wanted to, like, I was very curious. I was very intellectually curious. I think, like, I would just go around and like have a good time. I would definitely
already had the scientific method.
I definitely did not have the scientific method down. I did not understand. I had a lot of like concepts in my brain when I was a child that like I developed on my own to like help me to understand it.
Yeah.
So like I would often develop my own intuition on things that I wasn't like explicitly taught, and a lot of times, most of the time I was wrong.
That's okay. Being wrong means you're gonna learn.
Exactly. But like a lot of that actually ended up like helping me, like even now, because I was also an E&M girly all the way back in high school.
Yeah.
And now when I do plasma physics, that like E&M girly energy that I have is very helpful. Being
an E&M girly was not a good thing to be in high school. It was in college as a college physics major, but it wasn't super popular way back in the day. Anyway, where can people keep up with you or keep up with your research?
Yeah, I work with Anshul Kogar in the physics department. We work on condensed matter physics. There's a lot of like really cool and interesting physics going on, a lot of interesting and cool experiments going on in like the basement of PAB. So I guess
PAB is the Physics and Astronomy Building.
Oh yeah,
lovingly
my bad.
Called PAB by its students.
Yeah. The PAB. I'm always at the A level in the PAB, just blasting lasers. A lot of cool experiments go down there. Anshul Kogar, my PI, he's a very young PI, and I really do think he's going to make it big one day. So
you can find his website, right? Anshul's website.
I made his website.
Really?
Oh yeah, you did make his website.
Hello, webmaster.
So yeah, you could go to Anshul Kogar's website, see more of his cool research.
For me, I don't think you can really find my research like right now, because my experiment is this is kind of sounds like braggy, but it's like it's supposed to be pioneering.
Yes.
So it's supposed to be like kind of a first of its kind thing, and because it's not done, and
it's proprietary.
So you won't be able to find this information until the experiment finally succeeds in about like a year or maybe more, probably more than a year. Let's wait 2 years. But if the experiment succeeds, then it's a big deal for like my little niche.
Well,
of
in 2
physics.
years, if your experiment succeeds, you'll be the headline of every single newspaper anyway, and people don't need to look for you because we'll have solved nuclear fusion, and the entire world will be solved.
Yeah.
I would hope, but I don't think that.
Sometimes
one step, like we in physics we take like little baby steps, and I think like it's a pioneering baby step is what it is.
Sometimes I joke with my partner that like, you know, maybe like in a different life where you're more miserable and single, you would have
solved nuclear
you would
fusion.
have solved nuclear fusion, but like in this life have like such an amazing and incredible partner, and like your personal life is so fulfilling that I'm worried that I'm distracting you from inventing nuclear
Oh
fusion.
my gosh, JK, you're literally responsible for climate change.
Yeah. Maybe in a different universe, if we weren't together, there'd be nuclear fusion. But you know, maybe in this life, you still
I
can.
would be miserable.
That's true.
And so I'd rather live in this universe.
This person's a genius, by the way.
Okay, well, thank you both so much for being on the show. This episode was so much fun, and it was really great getting to know the both of you a little bit more.
Thank you for having us on.
Yes. And with that, never stop exploring.